Welcome to Senior High School Math Series. This time, let us have inverse of one-to-one functions under General Mathematics, Quarter 1, Week 4, and this is based on Curriculum Implementation and Learning Management Matrix for K-12's most essential learning competencies. Here is our lesson objective. Determine the inverses of one-to-one functions. Before we continue, let us ponder on this. If you are not willing to learn, no one can help you. If you are determined to learn, no one can stop you. Okay, let us have some recall. A function f is said to be one-to-one if and only if whenever a and b are in the domain of f. F of A equals F of B implies that A equals B, or equivalently, A is not equal to B implies that F of A is not equal to F of B. Another one, we had this theorem about the horizontal line test. We determine whether a function is one-to-one using the horizontal line test, and the theorem states a function is one-to-one if and only if every horizontal line intersects its graph at most once. Okay, let's proceed to our definition. Let f be a one-to-one function on a domain, perhaps restricted. The inverse function of f, denoted by inverse f, is the set of all ordered pairs of the form yx, where the ordered pair xy belongs to f. And by theorem, if f is a one-to-one function on a domain, then the inverse of f exists. Okay, so we can only have an inverse function if the function is a one-to-one function. That is according to this theorem. Let us apply using some examples. Let us have example number 1. Let f be the function described by the set of ordered pairs 1, 2, 2, 4, 3, 6. Find inverse of f and sketch the graphs of f and inverse of f on the same coordinate axis. So we follow the definition in our solution to this problem. From the definition, if the function is the set of ordered pairs 1, 2, 2, 4, 3, 6, then the inverse of f will have the ordered pairs 2, 1, 4, 2, 6, 3. Notice how the ordered pairs xy are switched in the inverse of f. 1, 2, x is 1, y is 2. In the inverse of f, it becomes 2, 1. The x coordinate now becomes 2, and the y coordinate now becomes 1. So the ordered pairs are simply switched. Let us have the graph of these functions. So we have for f 1, 2 on the rectangular coordinate system, 2, 4, and 3, 6. Now for inverse of f, we have 2, 1, 4, 2, and 6, 3. Okay, let us have this theorem. Let f be a one-to-one function on a domain x and range y. Then a function g with domain y and range x is the inverse of f if and only if the composition f of g of x equals x for every x element of y, and the composition g of f of x equals x for every x element of x. In some other books, this is called the property of inverse functions. Let us try for an example. Given that f of x is equal to x cubed minus 1 and g of x is equal to the cube root of x plus 1, show that g is the inverse function of f. To show that g and f are inverses, we use the theorem shown in the previous slide. So first, we get the composition f of g of x. We learned this in the evaluation of function. So to x in f of x, we substitute g of x, which is cube root of x plus 1. Therefore, we will have f of g of x is equal to the cube root of x plus 1, open and close parentheses, cubed minus 1. So cube of a cube root, we have x plus 1 minus 1. 1 minus 1 is 0. Therefore, f of g of x is equal to x. Okay, this is one part satisfying the theorem. Let us have the other. G of f of x. G of f of x is where we substitute f of x to x in g of x. 1. So now we have g of f of x equals cube root of x cubed minus 1 plus 1. Minus 1 plus 1 is 0. Then we have cube root of x cubed. Cube root of x cubed is x. Therefore, we satisfy the conditions in the theorem. We say that g is the inverse of f. Let us go to finding the equation of the inverse of a function f. Let f be a one-to-one function defined by the equation y equals f of x. The equation of the inverse of f can be found by the following steps. Exchange x and y. Solving y and equate y to inverse f of x. Okay? Remember, exchanging x and y, solving for y, and equate y to inverse f of x. These are three simple steps. Okay? For example, if f is a function defined by f of x equals 2x plus 3, letter A, prove that inverse of f exists. Letter B, find inverse of f. Letter C, sketch the graphs of f and inverse of f on the same coordinate axis. If we can prove that inverse of f exists, then we can find that inverse of f. And then we will graph the two functions on the same coordinate axis. Okay, let's start with letter A. Prove that inverse f exists. To prove that inverse of f exists, we must show that the function f is a one-to-one function. Let a and b be any two real numbers, and we assume that f of a equals f of b. Then, substituting a to f of x, and on the right side, substituting b to x in f of x, we have 2a plus 3 equals 2b plus 3. 2a equals 2b. Divide both sides by 2. A equals b. Hence, f is 1-to-1, and so the inverse of f exists. Another way to prove that f is 1-to-1 is to graph the function f of x equals 2x plus 3. We'll see that this is a linear function. And in the previous lesson, we used the horizontal line test to see whether a function is 1-to-1. So on the graph representing this line f of x equals 2x plus 3, if we use the horizontal line test, we will see that the horizontal line will intersect this graph at a single point. So f of x equals 2x plus 3 is a 1-to-1 function. Now that we know inverse of f exists, we can proceed to letter B. find inverse of f. So to find the inverse of f, we follow the steps, the 3 steps in the previous slide. So we write f of x equals 2x plus 3 as y equals 2x plus 3. And then we exchange x and y. So we have x equals 2y plus 3. See how the positions of x and y were interchanged in that step. Literally, y becomes x and x becomes y. At this point, we're going to solve for y in terms of x. So we subtract 3 from both sides. We'll have x minus 3 equals 2y. And to isolate y, we divide both sides by 2. That becomes x minus 3 over 2 equals y. And this now is the inverse function. We just need to equate y equals inverse f of x. So inverse f of x is equal to x minus 3 over 2. Okay, let us do letter C. Sketch the graphs of f and inverse of f on the same coordinate axis. So let us have the rectangular coordinate system. From f of x equals 2x plus 3, we know that if we substitute 0 to x, that becomes f of x equals 3 or y equals 3. So we have an ordered pair 0, 3 for f of x. And then this is an equation of the line where we know that this is in the form y equals mx plus b. So the slope is 2. So from this point 0, 3, we count 2 units going up and 1 unit going to the right, and that will be our second point on the line. And the coordinates of this is 1, 5. So this now is the line for f of x equals 2x plus 3. Following the way in finding the inverse of f, where we exchange the values for x and y in the ordered pairs. If this is 0, 3, then for its inverse, we will have 3, 0. And if the other point is at 1, 5, then the other point for the inverse of f will be at 5, 1. So this now is the graph for inverse f of x equals x minus 3 all over 2. Notice how these graphs of the two functions are positioned with respect to the line y equals x. And that will be taken in the lesson graphing inverse functions. Next, let us have example number 4. Find the inverse of the rational function f of x equals 2x plus 1 all over 3x minus 4. So again, we follow the steps in finding the inverse of f. We write the function as y equals 2x plus 1 all over 3x minus 4. And then we exchange the variables x and y. So we have x equals 2y plus 1 over 3y minus 4. Notice again, y becomes x in this step and x becomes y, literally. At this point, we're going to solve for y in terms of x. So we're going to isolate the variable y in one side of the equation. So how do we do that? We multiply both sides by 3y minus 4 so that it cancels on the right hand side of the equation. So we have x times the quantity 3y minus 4 equals 2y plus 1. Next, our aim is to isolate y. So let us distribute first x in the left hand side That will be 3xy minus 4x equals 2y plus 1. So we can transpose 2y to the left hand side by subtracting 2y from both sides of the equation, and then minus 4x to the right hand side by adding 4x to both sides of the equation. Then we will have 3xy minus 2y equals 4x plus 1. Again, going back to our goal of isolating y, so we can factor y in the left hand side using common monomial factor. So we have y times the quantity 3x minus 2 equals 4x plus 1. And finally, we divide both sides by 3x minus 2. After that, y is already isolated on the left-hand side of the equation. Y equals 4x plus 1 over 3x minus 2. And then for the last step, we equate y equals the inverse f of x equals 4x plus 1 over 3x minus 2. Next example. Find the inverse of f of x equals x squared plus 4x minus 2 if it exists. So from the function, we can already see, because the degree of the polynomial on the right hand side is 2, then this is a quadratic function. And this is a quadratic function. The graph represented by this function is a parabola that opens upward. So if we can remember the horizontal line test, if we do the horizontal line test to that parabola that opens upward, there will be instances where the horizontal line will touch the graph at more than one point. So this is not a one-to-one function. If this is not a one-to-one function, the inverse of this f of x equals x squared plus 4x minus 2 does not exist. However, the steps in finding the inverse of the function might work on this. Let us try. In the end, we will still see that the inverse of this function does not exist. Okay, let's follow these steps using this function. So first we will have y equals x squared plus 4x minus 2. Then exchanging the variables x and y, we will have x equals y squared plus 4y minus 2. Again, our aim here is to isolate y. So add 2 to both sides. We'll have x plus 2 equals y squared plus 4y. And then, how do we isolate y? We need to complete the square. Completing the square, we need to add 4 so that this is a perfect square trinomial. And adding 4 to the right side would mean adding 4 also to the left side. So that this now is a perfect square trinomial. Next, we have x plus 6, and this is now a square of binomial y plus 2 squared. Getting the square root of both sides, will get square root of x plus 6 equals y plus 2. And we know that the square root of x plus 6 yields a positive and a negative value. Then we'll have y equals, subtracting 2 from both sides, negative 2 plus minus square root of x plus 6. In here, the equation negative 2 plus minus square root of x plus 6 does not represent a function, because there are some values for x that correspond to two different values for y. For example, if x equals 3, y can be 1 or 5 if you try substituting x equals 3. Therefore, the function has no inverse function. Okay, let's proceed to example number 6. To convert from degrees Fahrenheit to Kelvin, the function is k of t equals 5/9 T minus 32 plus 273.15. Find the inverse function converting the temperature Kelvin to degrees Fahrenheit. Okay, so we write the function as k equals 5/9 times T minus 32 plus 273.15, such a way that k and T represents the Kelvin temperature at degrees Fahrenheit. In that case, there's no need to exchange the positions of the variables. So we have k is equal to 5/9 T minus 32 plus 273.15. We solve the equation for T in terms of k. So subtracting 273.15 from both sides, we have k minus 273.15 equals 5/9 T minus 32. To get rid of this factor here, 5/9, we multiply both sides by its reciprocal, 9/5. Then we have 9/5 times the quantity k minus 273.15 is equal to T minus 32. Then we can now isolate T by adding 32 to both sides. We have 9/5 times the quantity k minus 273.15 plus 32 equals T. So this is now the formula for degrees Fahrenheit in terms of the Kelvin temperature. T of k is equal to 9/5 times the quantity k minus 273.15 plus 32. Okay, for exercises on this topic, you can download from the link given in the description of this video. Thank you for watching. Please subscribe for more math lessons.